Welcome to the video on the extension of ether integrals via localization. So this actually will be the first part of two videos about this topic. One. So the motivation is, well, we developed already the ether integral with respect to Brownian motion for a fairly big class of integrants. But the motivation, the aim for today is, for this video is to define the ether integral from 0 to t, right? This is what we learned in the last video, of a function g. We'll define this object here, which is a integral with respect to the Brownian motion for any continuous function g. This is a rather natural class of integrants. And if you think about our motivating example in the introduction, well, this was a class we care about in mathematical finance. And now the issue is that in general, if I have a function g applied to the Brownian motion, this integrand here might not be in H2 anymore. So for example, take the function g to be just the exponential function for x of x squared divided by 2. Well, what we see then, that this, if I apply this function g to a Brownian motion, this will not be in our space H2, for which we learned how to define the ether integral. Right. So indeed, why is this not working anymore? Well, what we need for this to be in H2, we need that this is square integrable, right? This is what we need to ensure that this has to be in H2. But what we see, this can be infinite if t is big enough. So let's calculate it. I mean, we know what the Brownian, the probability distribution of the Brownian motion is. So let's calculate this, g square, right? This is g square, and now we plug in the probability distribution of the Brownian motion at time t, which is the normal distribution with mean 0 and variance t. This is the density of it. And now, well, we can simplify this by plugging in the definition of g, right? Then this is nothing else than this normalizing factor multiplied with the exponential function. Then have here 1 minus 1 over 2t multiplied with y squared. Right? And this is now, I mean, we integrate this over whole function, whole space gr. So this is infinite if we assume that, or if we have that t is bigger than 1/2. Right? If this is bigger than 1/2, this gets less. This is not negative anymore, so this is less than. This here becomes positive. Right now I have it. This becomes positive, and then the exponential function is exploding, so the integral is exploding as well. Okay. So this means in particular that we might not be able to integrate this function g. but actually it looks rather like a rather simple function. So we, of course, can integrate it, but we need to introduce another localization. And this is what we do in the definition 2.11. So in 2.11, well, here we go. We introduce now the space H2 which are all functions f mapping from the sample space omega times t to r, such that f is measurable as before. It's adapted, well, as an H2. And now we, instead of requiring the L2 norm is finite, we just assume that the integral from 0 to t of f squared ds is almost surely finite. Okay. And this is okay, the first part of the definition. Now the second part is increasing sequence. Let's call them new of 0 to t valued stopping times. Stopping times is called localizing sequence for function f in H2 log if we have the following two conditions are fulfilled. The first one is that if I consider f multiplied with the indicator function of 0 to mu n, this is an H2 for all n. And if I look at the probability that my nu n is equal to the terminal time t at some point, this is 1, right? So this basically only tells you that the sequence here of stopping times go to t, capital T, almost surely. So that's the definition. So this is what I call localizing sequence for f. Okay. So this is my new space. And the first two remarks, okay, let me give you two remarks. First one is, okay, my previous space H2 is obviously included in it. So remark 3.12 tells me, this is rather trivial. So that's always true that if all elements of H2 are also in H2 log, right? Because I relaxed here the integrability condition. If this term here is integral, and it has to be for L2, H2, then this is in particular almost surely finite. Okay, this direction is simple. And the next remark is this was our motivating example, right? For any continuous function R, g from R to R, we have that, well, if I apply g to my Brownian motion, this is now in H2 log. This is rather simple since B is almost surely bounded on 0 to t, right? So if you look at the sample path of a Brownian motion from 0 to terminal time t, it's a continuous function. And for a continuous function, you know it has a finite upper bound on a compact interval. All right, and now in the next proposition, you will understand why I call this space H2 log. Because if I have a function f in H2 log, I can always find a localizing sequence for f. Find a localizing sequence for f. Oh, let's call that mu f. All right. Right. So you see, if you have function f in H2 log, you can find a localizing sequence so that the localized function f multiplied with the indicator function of the interval 0 to mu n is in H2. Right? So you can localize any function in H log to be a element in H2. Of course, we have to prove this. Okay, so so if we have a function f in H2 log, we need to find a localizing sequence. So I want to define my nu n to be the infimum of the first time in my time interval 0 to t, such that the integral from 0 to t of f2 f square gets bigger than n. And now I take the minimum with t because I want that my stopping times are almost fully finite. Okay. Okay, so okay, this is my candidate for localizing sequence, and now I have to show you or convince you that these are indeed localizing sequence. So first thing I want to remark, because this is straightforward, I mean, this is an increasing sequence. Sequence, and well, each of the stopping terms are 0 to t valued. Yeah? I mean, this is basically by construction. Okay. So next step is I want to convince you that if I have this nu n, this is a stopping time. For every n in n. Okay. That's also not so hard because, well, what we have to observe here first thing, it is enough to verify that if I look at the mapping t to the integral from 0 to t of f2 square ds, this is adapted and continuous. And continues. Right? Why isn't this sufficient? Well, because if this here is an adapted and continuous process, I mean, this is a closed set, I mean, it's what this is. So this is a hitting time of a closed set, and then we know that the hitting times of closed set, if the process we are looking at is adapted and continuous, then it's a stopping time as well. Okay. Cool. So yeah, it's the first. If F is in H2, this is true, right? There's not much to do, because if you have simple functions, well, then the sums are continuous. We look at here, and they're adapted. Okay, that's straightforward. If H is in F is in H2, well, this is still true. It's true by the uniform convergence of integrals. Right. And last thing we need to make sure that if we have a function f in H2 log, well, this is still true. As we can again approximate it as we consider the approximating sequence, or by cutting off the function f if it goes below m or above m, this goes to 0, and this goes to f, well, by monotone convergence. So we can approximate the adapt, well, the f is a limit of adapted processes, so it's adapted. Okay. All right, second step. We need to ensure that this n is localizing sequence, or is localizing sequence for f, right? Well, okay, now we need to ensure two things. The first thing is we need to ensure that if I multiply f with an indicator function of the interval 0 to mu n, this is in H2. And then we need to ensure that these mu n's converge to capital T. Okay. So the continuity of my integral function see that, well, what we wanted to look at the H2 norm of f multiplied with the interval 0 to nu. Well, what is this? Well, this is nothing else than the expected value of the integral from 0 to nu of f2. Yeah, yes. Well, I stop here my nu in a way that this is the integrand here. So there's no, the inner integral is always less or equal than n. So I know that the expected value has to be less or equal than n. So in particular, this product here is in H2. Okay, and second thing, if I look at the union of over n of the set that nu n is equal to t, well, this is nothing else than saying my integral from 0 to capital T of f squared is finite, almost surely, right? has, so this event here has probability 1. All right. So indeed, for every function f in h log, we found a localizing sequence. Okay. And this allows us now to extend the E2 integral to elements in h log. Okay, so let's take f in h log and be localizing sequence. Localizing sequence for f. So then just the ito integral process. And this is a process in time from 0 to t is defined as the continuous process x such that this process, and this is what I want to define, is given by xt, sorry, xt, and xt is nothing else than the limit of n to infinity of my localized integrals. And so I take my f, I take my one corresponding localizing sequence, and I localize all the integrants, and then I see this is an h2, so these integrals here are well defined. So this makes sense, right? So this is, by definition of a localizing sequence, this is an h2. So this integral makes sense, and I would just say, okay, the limit is my integral process for functions in h2 log. Okay. Okay, the first thing we need to ensure now is that this definition makes sense, right? This is okay, this is the context of the next theory. All right. So this is theorem 3.15. So if I have function f in h2 log, then there exists continuous local martingale x such that for any localizing sequence, nu n for f, rules that the localized integrals, so the integrals corresponding to this localized integrals, yes, they converge to the process, the continuous local martingale, sorry, the continuous local martingale x almost surely. Right. So in particular, the E2 integral is independent of the localizing sequence of partitions, as you need in order to have this definition, right, which is given as limit, to be well posed. Okay, so this is what we need to prove here now. All right, so let's prove this. Proof. Okay. But I mean, first thing we need to do is to construct this process X. I mean, first thing, I mean, this is the main task, right? We need to find here this process and this continuous local martingale X, which has this property, right? Okay. Oh, what happened now? Here we go. All right. Okay. So let's write down a candidate. So okay. We have a function f in H2 log. This means also we have a localizing sequence for f. And sequence for f. Then we can define well, the approximating, so the xn, which hopefully approximates some limit x. And since we hope that this localizing, I mean, this limit is independent of the localizing sequence, it doesn't matter which one we pick here. Hopefully in the end, we'll see that this was okay. 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 And now first step is we want to convince you that these xn have a limit. Existence of continuous limit x. Okay. All right. Let's construct this. So first thing what we note, well, note if we define my capital N depending on omega, which is the minimum, so the first N in the natural numbers, such that my localizing sequence nu N attends the terminal time t. Right? We know that this is a finite number because what this is a part of the definition of localized sequence. Okay, so then let's look at the event omega 0, which is the event of all omega in omega, such that if I look at the sample part of the process xn, so the function t mapping to x and t, and I want that this is continuous, and I want that this is continuous for all n and m. Right? Then we know that this is the one set, right? Because for each n, this sample paths are continuous, and now I have a countable union of one sets, intersection of one set, sorry, countable intersection of one set. This is the one set again. And then I want to define another set, which is omega 1, which is just omega 0 intersected with the event that n is finite. Because here, this holds only p almost surely. So there might be another null set where this is not true. Okay. And well, now I can define my limit process, which is just given by x. And then the first time I hit the xn, which is the first time where my nu n attends the terminal time. And well, this works perfectly fine as long as I'm in this event omega 1. And otherwise, I set it just to 0 because this is not set, so I don't care. I mean, and this is all fine because we work here on a complete probability space, so I don't need to get nervous about measurability issues. So what does this mean here? So here this process x is continuous, and well, by construction we know that the limit of xn going to infinity is p almost surely equal to x. Right. So if we go back to our theorem, what we have shown is, well, we have already a continuous process x, which fulfills this property that the localized integrals here, they converge to the process x. Right? That's great. Now we have to do two things. We need to show that this process x, the limit process, is independent of the localizing sequence. And we want to verify that it's not only a continuous process, it's even a continuous local martingale. So let's do this. Step 2. Independent. Okay. Independence of the localizing sequence. Okay. If we want to show that it's independent of the localizing sequence, well, we take another one. So let's consider nu tilde. And this is another localizing sequence of partitions. Localizing sequence for f. And well, if we have another localizing sequence for f, we have another approximation. Let's call them x tilde n, which is now just the integral process. Where I localize with respect to nu tilde n. Okay. And well, what I want to consider now is I want to introduce a new, basically localizing sequence, which is tau n, which is just the minimum of nu n and nu tilde n. Okay. And now we know by the proposition 3.10, which was the persistency of identities, that if I localize here with respect, so if I look at xn and I localize it out from the outside with tau m, this is the same as x tilde n localized outside from the outside with the tau m, right? For n. Right? Because what we know is up to time tau m, the integrants of xn and x tilde n are identically the same, right? They coincide. So this means the integral processes coincide as well. Okay. So this means in particular that if you look at the limit of xn, it's the same as the limit of xm, x tilde n, at least if you're on this interval 0 to tau m. But this holds for all m. So that's actually very nice because, well, and now we just need to note that, well, since the tau m are given by the minimum of two localizing sequence of partition, this goes to T as well. Completes step 2. All right. Okay. Okay, so let's come to the last step, which is to verify that my process, my limit process X, is a local martingale. Is local martingale. Okay. Well, if we want to show that something is a local martingale, we need to find a localizing sequence of partition. So we introduce the localizing sequence, not of partitions, of stopping times, right? Localizing sequence of stopping times, right? And what is it? So we find sigma n to be the first times in the infimum of 0 to t, such that my integrand that stays low, it gets bigger than n, and then we want t to make it finite. Right? Okay. Okay. And now we just need to know two things so that this is indeed is a localizing sequence of stopping times. For first, sigma n goes to capital T almost surely if n goes to infinity. Right? This is simple to see because we know that this the interval from 0 to t of f square is finite. So at some point it has to be less than n for some n. That's nice. And we know that if I look at the stop process of x to time tau minimum sigma n, well, this is nothing else than the integral of f localized with respect to the Cato function of the interval 0 to sigma n dB. Okay. But this is a martingale, right? Is a martingale as this localized f is in H2. And then we know that it's a martingale if you look at Theorem 3.7. Okay. Right, so this is a localizing sequence for which the stop process is always a martingale. So we know that the limit process X is indeed a martingale. Okay. And now I would like to finish this video by extending the persistency of identity to our more general class of integrants, namely H2 log. Because we have seen that this was important to extend it, so this will be also a useful property later. So this is persistency. This is a persistence of identity. All right, so I have two functions f and g in H2 log. And I have a stopping time such that my f localized to the interval 0 to nu is equal to g up to this time nu. Okay. Then the integral, sorry, right, of f localized to nu equals to the integral of g localized to the interval 0 to nu. Okay. Okay, so the proof is not hard because we already know it for the class of H2, so we just need to extend the, I mean, we have seen this theorem exactly as it was before, just the new thing is that we have here the log. So we just need to take a localizing sequence for f and g and then extend the result to this new class of H2 log. Okay, that's not so. Introduce, define the stopping times, which is okay. Let's again call it tau n. This is a standard letter for stopping times, which is the first time to t. Such that we're either of these integrals, so either this integral gets bigger than n, or the same with the g goes, becomes bigger than n. Okay. And now, well, sorry, and okay, we define now. Right. But then now we can apply the proposition of persistency is persistence of identities for this simple, I mean, for the class H2, right? Because this is a localizing sequence for f and g. So what we have here is localized to nu is equal to the same just with G. Right? And then we can extend this by our last theorem to get the same for without the localizing here. All right. And so this is just, extending using a localization argument. What we have learned about the integral for function for integrand in H2 to now in H2 log. All right. Let me stop here, and I hope you enjoyed the video.